welcome back to the course on econometric modeling. Today I begin with module 19 is the first module under the part 4 which deals with statistical inferences. So, the first test we are going to consider is the t-test. So, module 19 on t-test. First of all, we talk about t-distribution. There are three important rules which we need to remember in order to understand how the t ratios are actually formed. So, if x and y are two independent random variables, where x is a standard normal variable, so it follows normal distribution with 0 mean and variance 1, y follows a chi-square distribution with k degrees of freedom, then x divided by root over y by k follows a t distribution with k degrees of freedom. So, this is our t ratio which is obtained as a ratio of a standard normal variable and a chi-square variable divided by k and the entire thing under root. So, if alternatively the other rules we need to remember are, first of all, if x follows a standard normal distribution, that is normal distribution with mean 0 and variance 1, then x square follows a chi-square distribution with 1 degree of freedom. And if x follows a standard normal distribution, then summation I running from 1 to n xi square follows a chi-square distribution with n degrees of freedom. So, a standard normal distribution when squared follows a chi-square distribution, and this chi-square distribution when summed up over n observation follows a chi-square distribution with n degrees of freedom. So, these are the three rules. Now, we know that one of the CLRM assumptions is U follows normal distribution with 0 mean and variance sigma square. We have also discussed this previously, that since beta hat is linear in the U, beta hat follows normal distribution with mean beta and variance sigma hat x prime x inverse. Alternatively, we can write it as beta hat minus beta, so I take mean to the other side, and then we have in the denominator the standard deviation of beta hat, which is root over sigma square x prime x inverse, and then this would follow a standard normal distribution, right. This x prime x inverse can also be replaced with summation xi minus x bar whole square when we do not write it in matrix form in the first place, and this is also the case when we deal with simple linear regression. So, we have only one independent variable, suppose the independent variable is x, then we would be writing it in this format. Both are the same thing, right. In case of multiple regression analysis, we use it in matrix form, otherwise in its simpler form, and both follow a standard normal distribution with mean 0 and variance 1. Now, we note that since U follows normal distribution with mean 0 and sigma square, so U divided by sigma or Uy, that is individual observations, will divided by sigma will also follow a standard normal distribution, that is mean 0 and variance 1. Therefore, as I have just mentioned that if x follows standard normal distribution, x square would follow chi-square distribution with 1 degree of freedom. So, Ui divided by sigma square would follow a chi-square distribution with 1 degree of freedom. And I also mentioned that x square when summed up from I equals 1 to n would follow chi-square distribution with n degrees of freedom. So, when we sum up this Ui by sigma whole square, I running from 1 to n, then this follow chi-square distribution with n degrees of freedom, fair enough. Now, suppose we call this y, where y follows a chi-square distribution with n degrees of freedom. We are denoting it by y because just in the previous slide I mentioned that if x follows standard normal distribution and y follows chi-square distribution, then with k degrees of freedom, then x divided by root over y by k follows t distribution with k degrees of freedom. So, this is something we are going to actually prove that how does it happen. Now, if y follows chi-square distribution with n degrees of freedom, then y by n by 2 would be summation I running from 1 equals to n u I hat square divided by sigma square is divided by n minus 2. So, we have this expression, this entire thing is divided by n minus 2. Now, you know that this u I hat square divided by n minus 2 is actually the estimator, sample estimator of the population variance, which we denote by sigma hat square, because this has also been already proved and mentioned that summation u I hat square divided by n is actually not equal to sigma square. This is a biased estimator of the population error variance. An unbiased estimator of the population error variance is n minus 2 when we have only 2 independent variables, or rather one constant term and one independent variable, right. So, when we are dividing it by n minus 2, we are replacing this thing with sigma hat square. So, this is y divided by n minus 2. So, in place of k here we are having actually n minus 2. Okay. So, now you can see that this is our x, which follows a standard normal distribution with mean 0 and variance 1, and this is actually our y by k or root over y by n minus 2, which follows a chi-square distribution with n degrees or n minus 2 degrees of freedom, right. Y follows a chi-square distribution with n minus 2 degrees of freedom, and y divided by n minus 2 would follow a t distribution with n minus 2 degrees of freedom. So, we are having actually in the denominator root over sigma hat square divided by sigma square, right. This is the thing. So, this is actually equal to root over sigma hat square divided by sigma square. So, sigma square when it comes out becomes sigma, sigma cancels out, and we have sigma hat square in the root over. So, this is how we have beta hat minus beta divided by root over sigma hat square divided by summation x I minus x bar whole square follows a t distribution with n minus 2 degrees of freedom. Okay. So, we are actually dealing with it with respect to a single independent variable, and the specific reason for this is that t statistic or t test is actually applied to test for a single hypothesis under the assumption that other things are actually not tested for. Now, talking about the PDF of the t distribution, it has a shape similar to that of the standard normal distribution, except that it is more spread out and therefore has more area in the tails. As the degrees of freedom gets large, the t distribution approaches the standard normal distribution. The figure shows that the PDF of the t distribution with various degrees of freedom, how do they move or behave. So, as you can see that the degrees of freedom increases, the t distribution actually behaves more like that of the standard normal distribution. It has a mean 0 and variance n divided by n minus 2 for n greater than 2. Now, talking about the t ratio that we have just derived, recall that while talking about inferences and test of significance approach, we introduced the formula of the test statistic of t test for the slope parameter as beta hat minus beta star divided by standard error of beta hat, where the null hypothesis is h naught is beta equals beta star. If the test is h naught is beta equals 0 and the alternative hypothesis is beta not equal to 0, then the test statistic will be replacing beta star with 0. I will be having beta hat divided by standard error of beta hat. The ratio of the coefficient to its standard error given by this expression is known as the t ratio or t statistic. So, just what we have just derived in the previous slide, that is called the t ratio. and depending on the value of beta under the null hypothesis, we will be forming our t ratio or t statistic. For a two-sided test, if mod value of beta hat divided by standard error of beta hat, we do not need to consider the mod value of standard error of beta hat, because standard error of beta hat should always be non-negative number, because variance is always a non-negative number. So, that is why we put mod value of only beta hat. If it is greater than t 1 minus alpha by 2 n minus k, where t 1 minus alpha by 2 n minus k is the 100 multiplied by 1 minus alpha by 2% critical value from the t distribution with n minus k degrees of freedom, then the null hypothesis that the coefficient is 0 is rejected and the coefficient, actually the associated variable, is said to be statistically significant. So, what we mean by this is that if we reject the null hypothesis, then first of all the coefficient is statistically significant, and having a statistically significant coefficient implies that the variable, the explanatory variable, is actually statistically significant, which implies that the contribution of that explanatory variable in explaining variations in the dependent variable is statistically significant, significantly different from 0. The value of 1.96, which would apply for the 95% significance level in a large sample, is often used as a benchmark value when a table of critical values is not immediately available. The t ratio for the test of the hypothesis that a coefficient equals 0 is a standard part of the regression output of most computer programs. So, most computer programs actually provide with the regression results the t ratios, and for large sample, since the t test approaches the standard normal distribution, so we can use 1.96, which actually corresponds to the 5% significance level of standard normal distribution, as also the 5% significance level for the t distribution, provided my sample is large enough. Now, we take an example of t-test in a simple linear regression format. Consider the estimates of the intercept and the slope from a simple linear regression with n equals 15. So, we have 15 observations. The standard errors are also given, using which we can calculate the t ratios as mentioned in the table. Note that if a coefficient is negative, the t ratio will also be negative, because standard errors are always non-negative numbers. So, my hypotheses are, we test them separately. Null hypotheses are alpha equals to 0 and beta equals to 0. So, my t ratios would also be alpha hat minus alpha divided by standard error of alpha hat. So, estimate of alpha hat is 1.10 minus alpha, which is 0, divided by the standard error of alpha hat is 1.35, that turns out to be 0.81. In a similar fashion, my t ratio for this parameter is beta hat minus 0 divided by standard error of beta hat, which is minus 19.88 divided by 1.98, and that turns out to be minus 10.04. So, in a t-test, individual null hypotheses are tested separately, as I have already mentioned. The test statistics would be compared with the appropriate critical value from a t distribution. I have a t table just in the next slide. Here the number of degrees of freedom is given by 15 minus 2, that is 13, and the 5% critical values for this two-sided test is actually 2.5% in each tail, right. And you can see that from this table, this is my two tails. I have 5% significance level corresponding to 0.025 one tail values, that is 2.5% in a particular tail, and as shown in the previous slide that my degrees of freedom is 13 and minus 2 is 13. So, corresponding to this I have 2.160 at 5% level of significance at individual tails, and if I consider 1% significance level, then my critical value is 3.012 for individual tails. So, you can see that this is 2.160 for 5%, and while the 1% two sided critical value is 3.012, just as we have observed from the table. Given the t ratios and critical values, H naught alpha equals to 0 is not rejected, since our calculated value 0.81 actually lies in the acceptance region or non-rejection region rather, I must say. So, this is my distribution, and this is at 2.5%, 2.5%, 2.5%. The values are minus 2.16 and 2.16. Since it takes a value of 0.81, it actually is somewhere here. So, it falls in the non-rejection region. We do not reject the null hypothesis, but H naught when beta equals to 0 is rejected, because the calculated value minus 10.04 is actually less than minus 2.16 and of course less than plus 2.16. So, minus 10.04 will be somewhere here in the rejection region, and that is why the second null hypothesis or the null hypothesis concerning beta is rejected. So, this is the t table that I had just used. I just want you to note that this t table has degrees of freedom up to 22. The rest of the degrees of freedom of this table will be presented in a later slide. Now, the implications of the test results: if H naught is rejected, it would be said that the test statistic is significant. So, which implies that beta hat is significantly different from 0. If the variable is not significant, it means that while the estimated value of the coefficient is not exactly 0, for example, in this example alpha is 1.10, right. My alpha value is 1.10. What the null hypothesis? We have not rejected the null hypothesis, where the null hypothesis is alpha equals to 0, but alpha hat actually takes a value which is equal to 1.10. So, if the variable is not significant or the estimated coefficient is not significant, it means that while the estimated value of the coefficient is not exactly 0, the coefficient is indistinguishable statistically from 0. So, statistically it is not significantly different from 0. If a 0 were placed in the fitted equation instead of the estimated value, this would mean that whatever happened to the value of that explanatory variable, the dependent variable would be unaffected. This would then be taken to mean that the variable is not helping to explain variations in y, and that it could be therefore removed from the regression equation. Now, we take another example of t-test from a multiple regression framework. So, let us consider the earnings equation of Ambrose. The paper or the study was conducted or published in 1987, where he considered 428 married working women, and the equation he estimated with a large number of data. So, the data actually consisted of more number of women, but out of them 428 were working. So, this equation specifically pertains to only those women, those who were working, and their number was 428. So, the equation is log of earnings is a function of course the constant term plus age of the women, then polynomial or an age square is also considered. Then we have education and number of kids, or the presence of kids rather, whether the family has kids or not. It is actually not the number of kids, whether the woman has kids or not, plus an error term. This is the framework of the equation. The regression results are given as shown in the table. So, r square value is observed to be 0.04, which is actually very small, and this r square is based on 428 observations. And these are the variables, their coefficients, their standard errors, and the t ratios that are being calculated, right. So, what we observe? There are 428 observations and 5 parameters. So, the t statistic have 428 minus 5, that is 423 degrees of freedom. For 95% significance levels, the standard normal value of 1.96 is appropriate when the degrees of freedom are this large. Now, I show you the table with degrees of freedom 22 or more. So, we are having here sample size which is 428. Degrees of freedom pertaining to 100 is mentioned here, after that it is equal to, it actually goes to 1000. Now, again if I consider 2-tailed significance level of 5% and 1-tailed significance level of 2.5%, then you can see that pertaining to 1000 this is actually 1.962 for 1000 observations, right, and this is so close to the standard normal critical value which is 1.96. So, that is why we can consider it to be 1.96. When the sample goes large, the t distribution actually becomes equivalent to the standard normal distribution, and these of course represent the confidence level. Now, you can see that for 95% significance levels, the standard normal value of 1.96 is appropriate when the degrees of freedom are this large. By this measure, all variables except for the constant term are statistically significant and signs are consistent with expectations. So, we will not get into the signs as we are not actually discussing the economic implications of the variables included in the equation, but provided that my critical value is 1.96. So, you can see that all these estimated t values or t statistics are greater than 1.96 except for the constant term. All the estimated coefficients are statistically significant. Statistically significant implies that they are significantly different from 0. So, this is how we understand t ratios and t test in multiple regression framework. These are the references that I have followed. Thank you.